Welcome back. This time we will talk about the addition of oxygen, creating compounds known as epoxides or electron deficient carbon centers known as carbenes. To start, let's first analyze the three-member ring that you see here. If you change one of those carbons for an oxygen, you get what we call an epoxide ring. An epoxide is a more general term to express this type of ring. This is also known as oxirane, which is a common name, and oxacyclopropane, which is the proper IUPAC name of naming this ring. Oxa for the oxygen present, cyclopropane to tell you that you have a cyclopropane structure present in here, but one of the carbons has been replaced by an oxygen, hence the oxa prefix. The way in which one goes by synthesizing epoxide compounds is by the use of organic peroxide molecules. Typically, this will be an organic carboxylate or carboxylic acid peroxide. And one of the most used versions of the carboxylic acid peroxide is the following: m-chloroperoxybenzoic acid. This specific compound, and you can see here I have a color label a few of the letters, is also referred to as m-CPBA, right? And it's basically those particular letters just kind of brought together as an acronym. m-CPBA is rather useful to us because it turns out that for this molecule the melting point is 92 degrees Celsius, and what that means is that for most common temperatures at which you're going to perform experiments, this material will be present as a solid, and solids are easy to handle, they're easy to measure, and pour into containers. And even when you find it impure, if you have an impure sample, one that has only 77% purity or less, even in those cases the melting point is still up to 69 degrees Celsius. So even in those cases you will still have a solid. So it is a convenient molecule to use. Now the mechanism is simple, but at the same time a bit complex, because everything happens with just those two molecules at once. And technically, like we saw already in the addition chapters, is that the alkene approaches the electrophilic element, which in this case is the oxygen right here. And you can think of it this way: that oxygen is bound to a carboxylate functionality. And that carboxylate functionality is withdrawing electron density away from this oxygen, making it semi-susceptible to attack by nucleophiles. In addition to that, you have that oxygen-oxygen single bond that is rather weak. So this is a prime target for attack by nucleophiles. And so that's what happens here. The alkene attacks that oxygen. In the process, that oxygen-oxygen bond is broken. Specifically, those electrons move over here to create a new bond between oxygen and its adjacent carbon. That, of course, means that the double bonded carbonyl group that we have here has to have its electrons move out of the way onto the oxygen. And then what ends up happening is that this oxygen, which is strategically positioned next to that hydrogen, is available for attacking the hydrogen. And finally, that OH bond set of electrons goes into attacking the other end of the alkene. And this is all a single cycle that takes place at once. So it's not like you have the one electron set moving first and then the other and then you have the new intermediate. No, this whole thing is all one thing. And in the process of that, what ultimately happens is that you create a double bond over here, as you can see in the picture there. The oxygen right here acquires that hydrogen, as observed right here. And of course, this double bond has become a single bond. Once again, we observe that here. But the main result that we're really looking for is what happens to the alkene. And all that the alkene really does is acquire an oxygen atom. And I mean that quite literally, because you are taking up that oxygen, but it is an oxygen atom, neutral in charge. It only has 6 electrons. To complete this octet, it acquires 2 electrons from the pi bond of that alkene, And then the other two electrons that used to be part of this OH bond are used to complete the cyclopropane structure of the oxirane ring. Now, one feature that also needs to be mentioned is that when you're dealing with alkenes that have some type of stereo isomerism, specifically the trans and cis isomerism, that is translated from the alkene onto the epoxide ring. So when you react your m-CPBA with your trans alkene, you end up producing trans epoxide rings. All right, so notice here that the carbon on the left has the ball bond, the carbon on the right has the dash bond, and that's exactly how we end up with on a product here. We have bolt on the left, dash on the right side. And of course, because the alkene is planar, there's no reason why this has to attack from the top portion of the molecule. It could easily attack from the bottom, in which case this will be the geometry that it will observe. And right here you will get the same retention of configurations, namely that the carbon on the left side will now be dash and the one on the front will be bolt. And so in essence, in this reaction, if you are creating stereo centers, you will produce the racemic mixture of both enantiomers. Okay, now there's another way of preparing cyclopropane rings, and these ones will be fully composed of carbons. And the way this happens is with carbon that already has a lot of halogens on it. In other words, a carbon that is making the carbon-hydrogen bond slightly acidic. Acidic to the point where you could even treat it with a relatively mild base from the point of view of organic chemistry, hydroxide. In essence, hydroxide can remove the proton of chloroform. The electrons can be pushed onto the carbon that's stabilized. So this carbon ion is stabilized partially by having the three chlorines with electron withdrawing abilities, in essence decreasing this negative charge. But then what happens is that you create this salt, and the potassium ultimately abstracts one of the chlorides to precipitate out as potassium chloride solid, and you end up forming this electron deficient carbon that does have a formal charge of 0, but it has an MTP orbital. It's electron deficient. This is known as a carbene. And here you can see an orbital picture. So you have the lone pair on technically a sigma bond, but over here you have your MTP orbital. And so this creates a little bit of activity for reactivity, I should say, for interactions with alkenes. So once you produce that carbene fragment, it can react with your alkene to produce cyclopropane rings like the ones we saw with epoxides, but this time around every member of the cyclic structure is a carbon. And the idea is that the lone pair of the carbene attacks one end of the alkene carbon, the other alkene carbon attacks with the pi bonds, closing the cyclopropane ring. And this can happen from the top or the bottom portion of the alkene molecule. Therefore, you get mixtures of enantiomers 50-50%, in other words, racemic. And there is one more way to make this happen. It doesn't have to be with chloroform. You could actually, especially if you don't want to have chlorines stuck on your cyclopropane ring at the end, you could perform the Siemens Smith reaction. And what you end up doing is utilizing methylene iodide, meaning that you have two iodides on a single carbon center. This particular molecule is light sensitive, so if you do use it, you have to, store it in the dark, cold temperature. So you basically a freezer, and you have to make sure to either wrap it up with aluminum foil or use a container that is opaque so that no light is going through it. But if you have the intact material, you can react it with zinc metal. And what happens is that zinc technically has these two electrons that are ready to be given off, specifically the 4s2 electrons. And you could think of it attacking almost like a nucleophile. The electrons are given to the carbon, then the carbon iodide bond is broken, and the iodide is delivered to zinc. So you create this structure right here, which has halogen, zinc, carbon, halogen. And then when the alkene approaches, you can attack via the red bond right here, the carbide bond, which is technically mostly centered on the carbon more so than zinc. And so that can attack the alkene, and you can once again do it from the top or the bottom face of the alkene. Then the pi bond of the alkene attacks that very carbon to complete the cyclopropane ring structure, and that of course means that the iodide has to take off. And once it does that, it combines with zinc that already has one of the iodides to give you zinc iodide as a precipitate, and in the process you once again form your cyclopropane ring. And if stereocenters are present, you will form the racemic mixture. Okay, so this completes the story for the synthesis of epoxides and carbenes. In the next video, we'll talk about the addition of water onto alkene molecules. And there's 3 different ways of doing it. So we'll have plenty to say about it. So I will see you in the next video. Bye-bye.